Welcome to this exercise session where we will be solving the following rotating thin disk problem. The problem says something like this. A thin disk of 900 millimeters of external diameter and 150 millimeters of internal diameter, like this one depicted on the right, rotates about its axis, meaning this one here, let me mark it here, O here, at 3000 RPMs. The disk density is 7,800 kilograms per cubic meters, and we need to use Poisson's ratio 0.3 value of it. So we're being asked four things. So the first one is calculate the circumferential stress in the inner and the outer radius, meaning what is the value of this stress at this point in here and this point in here. So we can mark it as, for example, sigma theta 1 and here sigma theta 2. The second question is, what is the radius at which the radial stress is maximum? Yeah. So meaning in this section, or what they're asking is, you choose another color. Along this line, it says where we're going to find the maximum radial stress. Third is what is the value then of that maximum radial stress? And fourth, we need to plot the variation of the circumferential and radial stresses along the radial direction. And we are being asked that the stresses should be plotted on the horizontal axis, and then the radius value should be plotted on the vertical axis. I have already written here the equations for the circumferential stress and radial stress for a thin disk with a central hole. So meaning we don't have to derive from the general equations to adapt it to this specific case where certain boundary conditions apply. As in the lecture, it was mentioned that, for example, the principal boundary conditions that were in force here were that the radial stress was 0 at the position of R1 and position of R2, meaning in the inner radius and outer radius, because there was nothing applied to it externally, then the radial stresses were 0 on that part. Now, let's start solving one by one. And as a helping software, I'm going to use Python to write down the equations, substitute some values there. And also at the end, it would allow me to plot the variations of these stresses along the radial direction as is being asked in point number 4. So I will ask you to stay with me because we're going to do both. So even though if you haven't used Python before, so it would be a nice experience to see how, or one of the ways it is done. And you could also use it in another place, for example, if you want to have it as your own Python library, for example, to calculate stresses on thin rotating disks or rotating thin disks, for example. So let's go ahead and stay with me because it's going to be very interesting. So for the first point, the circumferential stress at the inner and outer radius. So one of the things we need to do is just take this equation and let's call it equation 1 here, and this one we're going to call it equation 2. So we need to take equation 1 and then substitute whatever we see, the value of R here and here, by the corresponding value of that point where we want to calculate the stresses. So in this case, it's going to be R1 and R2. So just to have a clear equation of those, and let me mark here that we're going to work on answering question number 1. So here. So we're going to have that, for example, this sigma theta 1 is going to be what? Well, I'm going to just make the exercise of writing the whole equation because it's going to be beneficial in the sense that we will have it then there. And you could use it later on in any other application you need to. So this is going to be this 2R2 plus R1 plus this term here. But now this R turns into R1 because we're talking about, so I should mark it here as inner radius. So let me delete this part and then say inner. And continue here like square minus R1 square, because remember, we want to calculate this stress, meaning this one here, in R1, times these terms here, basically, and divided by this term here. Perfect. We can do a little bit of simplification. For example, we know that this is going to be simplified with this one. And let's see what else. So we could do certain simplifications here if we needed to, or we can just leave it as it is and call it, let's just write it down again completely, the reduced version, like this. 3 plus Poisson's ratio, and then we can multiply it by this one. 2 square, R1 square, plus R2 square minus this one here. So it was a very mild simplification we did here. and then this term here. But what this is going to help us do is to now find out what's the value or what's the corresponding expression for the outer, meaning what's the value of this circumferential stress on R2. So following the same logic like this one here, so I can just write it down directly as something like this. So it's going to be equal to this constant, well, it's not a constant term, well, at the moment it is, but it may vary like this. And then again, this is going to be multiplying this term here, this is going to be the same. Now, in this part here, so instead of using R1, we're going to use R2, meaning that here we're going to end up with R1 minus, and then here we're going to end up with R2 plus this one here. Yeah, divided by 3 plus Poisson ratio. And that is, so now we have the two equations, and I could just single them out. So we know that we're using this one here, and we are using this one here. So we could substitute the values, and then, because we already have values for all of these terms, and let's write them down here. For example, in here, parameters. So we have the density, different color. Density that is equal to 7,800 kilograms per cubic meter. So this is important to notice that the units we're using here are kind of in different scales, to put it in that way. But for example, if we're using density in kilograms per square meters, then we know that we need to operate with the diameters or radius, then we would need to change either one of those to match the same units. So let's change diameters to meters, and then we will have everything at with the same type of length unit. And then also this 3000 RPM. So let's turn it into something we could use it together with these other two or let's say parameter variables. So let me write this one. So this one, then Poisson's ratio is non-dimensional. Then we have R1. R1 is half of the inner diameter, which is 150 millimeters, like this. Well, half of this, delete it. So it's going to be 75 millimeters, which is equal to 0.075 meters. Then we have R2, that is 900. Again, no, this is 450 millimeters. And now just take a look at these dimensions. So a disc of 900 millimeters rotating at 3000 RPM. So that's quite something, because 900 millimeters is close to a meter. So just mentally imagine a disc of a meter diameter rotating at 3000 RPM. So it's something, let's say, to be careful with. Let's put it in that way. And then this is going to be equal to 0.45 meters, sorry. And then these 3000s, the angular velocity, 3000 RPM. So we need to turn it to radians per second, which means that we need to multiply this by 2 pi divided by 60, radians per second. Let me write radians. All right. So seeing this, now we have all the values to introduce in these two formulas and get answered for the first question. So let's do that. But to do that, let's jump to Python, and let me just change the editor here. There it is. I have it, well, not completely prepared, but I have something there. And let's see. This is exercise 1. I have the description of the exercise here. So we're going to solve the first question, which is to answer what is the circumferential stress at the inner and outer, let's call it radii. So there are a couple of those radiuses also. And then I believe it's like that. Yes, let me just check. Yeah, radii. Yeah. All right, then we have this. So I'm using some numerical libraries, some symbolical libraries, because I would like to work with symbolic libraries before plotting things. I have some plotting and some utilities to display nice equations here. So let's start by doing this. Let's build those two equations, or that equation basically. But to do that, let's define what are the variables we're going to use there. So we're going to have R1, we're going to have R2, we're going to have also the density. I need to write it like this. I need to write the Poisson's ratio, which I'm going to write as new, then angular velocity, and a variable, something that needs to change so we can use it in other ways. So what I'm using Copilot here, so it's very fast too, and it understands certain stuff. So I'm just going to press tab, and then I have already what I wanted to have. And then but this is going to allow me to use these symbolic variables into the equations I'm going to use. So I don't pretend this to be a an exercise session or tutorial on Python, but I need to do this in order to get the results I want to show you. So let's continue. So let me run this one here, and let's add another line of code, and then let's create, let's say, the circumferential stress function or class. So we're going to have a class. It's a class. So a class, and let's give it a name of circumferential stress, and this is a class of type function. Perfect. And then I need to use this decorator. Look at this. So it's giving me something, but I don't need this part here. I don't need this class method. I need to define the evaluation of that function. Please, this is not part of what you need to do, but I needed to, so I can show you things as I mentioned. So I have to use R1. Sorry about that. Maybe I can do all of these, and then I can write these equations. I'm going to use, you're not going to see, but I'm going to use the equations I have in the notebook, and this is going to be something like this. So it's going to be density times angular velocity square, and this is divided by 8. Yes, and then I'm going to multiply this by this 3 plus nu, and then I'm going to multiply this by the big kind of, not parentheses, but yeah, but these terms that were repeated here. So we have R2, sorry about this, so R2 square plus R1 square, that's the first term, minus the second term, which is R1 square times R2 square, and then this is divided by R square. Awesome. And then this is also, I need to subtract from the term that is, let me put it like this, R square. It's giving some suggestions that, well, definitely I don't need that, times 1 plus 3 times Poisson's ratio, and then this is going to be divided by 3 plus Poisson's ratio. And I believe I have it. Yes. So if I want to print it to see if it's the same equation that I'm using in notebook, so I need to use these utilities, display math. So look at this. It understands all of this. So let me see if it works. Yeah, there it is. So I have that the circumferential stress equals to the density square of the angular velocity divided by 8, and then these two terms added. So this seems to be quite okay if I compare to one node here, so this general equation here. That is awesome. Yeah, it looks like we have a match there. Yeah. Okay, we have the plus sign, and this is not correct. So this should be R. Yes. So if I run this, I should have, let me see, check. Yes. Yes, this is correct now. It's R and R here. Okay, now let's write down the problem data. So we're going to have, I'm going to write them differently. So this is going to be 0.075 meters. Awesome. Then R2 is going to be equal to 0.45 meters. Yeah, that's correct. Density, I'm going to call it like this, and that's going to be 7,800. Yes, correct. We go down. Wow. Poisson's ratio numerical, it knows. And then the angular velocity, let's turn it into radians per second from RPMs. So it's 3,000 RPMs times 2. Yeah, this is correct. This is correct. Perfect. Yes. Now let's calculate at inner and outer radius, and then, well, I have it here, it knows, and I have it here, so it also assumed it, and then I can, yeah, I can display them nicely if I wanted to. Let's see how it goes. So if I run this one, oh, look at this. So the inner circumferential stress at the inner radius is this much, and this is going to be in what? Let's say this is going to be in pascals. So we have here 3, and then 3 more here, so 129 megapascals. So let me write down here, sigma theta inner is going to be equal to 129.367, let's call it pascals. Yeah, and then this one too, outer is going to be, let me count this one, this is 3, and then this is going to be 30.853. Let's call it like that, pascals. So these are the results. So let's go back to to OneNote and write them down. Here it is. Yes. So sigma theta at R1 is going to be equal to, we set, let me just quickly check, is 129, 129,367. So it's going to be 129,367 pascals. And sigma theta at the outer radius is going to be equal to, and look at this, is 30.853 pascals. And we have our first solutions. I'm going to mark them here. Awesome. So we had the formula here, formula 1, and what we did was to substitute the value of r to the corresponding inner radius and to the corresponding outer radius, and that was it. So it was very easy to find the answer to the first question here. Now, let's find the radius at which the radial stress is maximum. And okay, so it means that we need to find radial stresses is ruled, or we can calculate it by using equation 2, meaning that we need to operate with this one here. Now, let me just copy this one here. And let's say question number 2, r, where sigma r is maximum. Yeah, so let's put it here. So to understand or to see where this equation gives us or points us at where the radius or where we should be standing so we get the maximum radial stress, it means that we need to work with this. The derivative of this radial stress with respect to r should be 0 at the point, because that represents a change on all of this, kind of a maximum of a minimum or a minimum. So it represents a change, a point there. So to understand that, so what we need to do then, let's derivate this. And when we derivate this equation here, so we need to know that this could be handled just by derivating the internals of these brackets here, because this is practically constant there. So no point in wasting time using the chain rule here, because we know that we only need to multiply this for whatever the derivative of this term within brackets is. So let's do it. So this is going to be equal, and let's continue working with this, like this. And let's see the derivative of this part here. That's equal to, well, I said that this term is going to be kept equal 8, 3 plus the Poisson's ratio, and then derivative of this, and this I'm going to write. So the derivative of these terms in these parentheses are going to be 0 plus 0, because r1 and r2 are constant, so they don't change in this case. And then the derivative of this part, so this is r to the power of -2, we can write it down. So this is going to be equal to r1 square, r2 square, divided by r power of 3 times -2. And then this is minus what? Well, 2r. And this should be equal to 0. So assuming that density exists, that is rotating, and for sure that there is a Poisson's ratio, then I can take all of this and send it to the other side of the equation, because this should be equal to, here, 0. And then I'm going to end up with this, so minus and minus, so I'm going to have r1 square, r2 square, or 2 of these. And then this is going to be divided by this, power of 3, minus 2r equal to 0. Then I can put all r's, not r1, r2, but all r's at one side of the equation, and it should be something like this. So if I send this to the other side and then multiply by the other one, it's going to be, yes, so actually at this point I could get rid of these 2's here. I can say, well, r to the power 4 equals to r1 square, r2 square. Then it means that then r square, just step by step, equals to, sorry about this, to r1 plus r2, which means that the position where the sigma or the radial stress is going to be maximum, let me write it correctly, max, is going to be in r equal to square root of r1, r2. Right, so let's calculate this one. So let's go to Python to check what is the value of this r. Let's go. Let me jump here. Okay, so let's create another one, and it's going to say, we're going to say radius where maximum, radial in this case, of course, and that's going to be what? Look at the, oh wow. Let me give it a try to this, and let me just print it out. Display. Well, no, that's one of the solutions. So if I found all of the solutions, so which one should they be? So we have the imaginary terms here. So we have these ones here. No, okay. No, this is nonsense because this is the circumferential stress. We haven't written the equation for the radial stress, but we could write it and see what's happening here. So let's go back here and let me write down the equation, the class for the radial stress. And then I'm going to have a class method. So let me see something like this, but in the terms, this is going to be plus, and this is going to be minus, and then this is going to be minus this one here. It's very easy to remember. Yeah, and then I can display them both here by telling, there you go. Let's see. Yeah, this looks correct. So I have r minus r, I have minus this quotient here, and then plus and plus. Yeah, it makes sense. Now I could use this one here. Sorry about the delay, but this is pretty interesting. Let me see. There it is. Here it is. So any one of these. So let's grab the latest one, the last one. Actually, this is 3. This one. This is where we should be. Let's say we'll have that. Perfect. But I could just write it down, kind of R max. Let me check this. What does it does? No. R max. I'm not going to waste more of time, so I have to that this square of this one. Oh boy, this is scary. No, but I don't want this, but I just want to display this one. There it is. And this is in meters, so 0.183 meters. So let's go back to one node. 0.183 meters. There it is. Answer to the second question. Third question, well, now give me what's the maximum radial stress. So for the maximum radial stress, let me write it down here. Where am I here? Maximum radial stress is basically doing this. Let's call this R max, where R max is located. Well, this R max is because the radius of the maximum radial stress is not that it is the maximum radius. I should. Yeah, let's leave it like that. Then it means that I need to grab this equation. And substitute that wherever it is, this radius, so it supposed to be something like this. So let me just write for once, it does kilograms per square cubic meters times, I believe the results of this, just a quick check, how much is the angular velocity, the numerical value. How much is this? Just a second, just doing a quick calculation offline. It's 314.15. So this is going to be 314.16, 1 divided by seconds, or radians per second. And then this is divided by 8 times 3 plus 0.3. And then I just need to insert these values here. Those are, R2 is 0.45 meters, this is square, plus 0.075 meters square, minus multiplication of these both, square times 0.075 meters square, and this is divided by these values here, 0.813 meters square, minus this same value here, 0.183 meters, and all of these square. There it is. Then it means that the sigma radial maximum is going to be equal to, and let's go back to our calculator here. So this is where I calculate this. So this is going to be maximum radial stress. Wow. Evidently, this one. Let me display this one here. So yeah, it's going to be, how much is this? So it's going to be 3 and 3 more. So it's 44.65. What is that? Pascals, actually. Well, it's meganewtons per square meter, and that is pascals. So let's go back to one node. Is 44, sorry, 0.656 pascals. And let's mark it down. So we found the answer to our third question. Here, what's the maximum radial stress? By using the position where the sigma, or where the derivative of the radial stress with respect to r is equal to 0. So we found the maximum, or the radius where that maximum happens, which is 0.183 or 183 meters, so 183 millimeters. And then we substituted that into the equation of radial stress, and that's going to give us the maximum radial stress. Let's go with the fourth point. And the fourth point is to plot these two values of variation of circumferential and radial stresses along the radial direction, meaning we need to build here a plot. You could use any software. You could use Excel, you could use it by hand, you could use, I don't know, any other MATLAB, GeoGebra, any other thing to plot this. Doesn't matter. You should get to the same results. Plot, say, sigma r and sigma theta, so radial circumferential stress versus radius. Yeah, so let's plot that. So you could go ahead at this point, because I'm going to write the code to plot these two lines to these two stresses. And it may get a little bit kind of lengthy, but you can just jump to more ahead, so where you get the results, or you can stay with me here and we could build it together. If you're following along, for example, writing down this Python code, also you could do it, and then you can just write along with me, and then we can have a nice, let's say, Python exercise in that way, in that sense. So to that end, we need to calculate a few things first. So let me write down here, plotting radial stress and circumferential stress along the radius. There you go. That it is. Perfect. So we need to do a few things. First, we need to have one symbol that defines any position on the radius. And let's call it r. And that r is going to be a symbol. Yeah, r. That's correct. And then we're going to create expressions for the circumferential and radial stresses based on the problem parameters we already have. So meaning we're going to get the exact formula for it. So let's call it, like, for example, circumferential stress expression. Let's call it like that. And that's going to be equal to, that's close to correct, but it's not this, the circumferential stress. Now that's why we created this method here called evaluation, or eval here, dot eval. And yes, we need to use all of those symbols there. That is correct. This saves a lot of time. Then let's do the same. Just a second. Circumferential, yeah, and then radial. You should understand that I want the radial stress. And let me just check that this is what I want. Radial stress. Yeah, that is correct. So yes, this is what I want. Perfect. What else I want? Okay, now I want those. Now I need to create a vector that contains values for circumferential and radial stresses along different points in the radius. So I should start from 0.075 up to 0.45, and then split that into several points, and then find the values for those two stresses along those points. So let's call then a vector of values. And yes, that is correct. And I want to have a vector from R1 to R2, let's say 100 points along those two, let's say along in between those two values. That's correct. And this helps a lot, this AI, let's say, helper. Then yes, I want to calculate those values. That's correct. And then yes, I want to calculate these values on the radial stresses. That is correct. Let me run this. It should run perfectly. Yes, it has it. Yeah. But then something I need to do, because I know that this needs, if I want to plot them, I need to turn these let's say results into, make sure that they are floating point values. So it means that I need to grab all these three and say, well, our values. And I don't need to append these, but I'm going to call them float, and then it should understand what I want to do. Yes, that's correct. That is correct also. And that is correct also. Yeah, this definitely saves time. Awesome. So let me run this again. Yeah. Now let's write the code for plotting, yeah, using plotly. Yes, because I already defined it. Let's call this finding the vector of values. Yeah. Awesome. So let's do it here. So now we need to define our charts or figures. Our figure is going to be a go figure. That's correct. And then we need to add some data in here. Oh, look at this. So scatter, yes, that is correct. But I need two sets of data. Yes, I need this one, and I need this one. Now this is here that I need to have two plots, or two types, two plottings. So scatter plottings, yeah, that's correct. So the values of the radius in the horizontal axis, the values of the circumferential stress in the vertical axis lines. These are for the labeling purposes. But actually, what I want is that the radius are in the vertical direction and the stresses are in the horizontal direction. Yes. And let me give some colors here because this is not giving me the kind of some different colors. So let's see here. Let's put this line, like a dictionary. No, let's call it just red. Okay, now this is a color that I want. I don't want any dashing. Red. Perfect. Let's continue. So I could, right away, I believe I could try to show these values, but to do that, I need to add certain, labeling to the chart, like, what's the title, what are the axes and everything. So to do that, after we have created that value, this is already giving me this. Okay, let's see. Let's check it out. So we have the title. So we have the x-axis. In the x-axis, we have stresses. Yes. It's in Pascal. Yes. We have the radius in meters. Yes. But something I want to do is that everything starts at 0, at least, let's say, the x-axis starts at 0, because now the x-axis is starting at 0.075 up to 0.45. So I just want to force it to start at 0 so I have a better representation. To do that, I'm going to go x-axis, axis, yes, and then this needs to be passed as a dictionary. I'm going to have a range. X-axis, well, yes. Actually, yeah, let's force the x-axis, the stress axis. Yes, so it's a range that is going to go from something that I don't know yet, because, well, I need to find what's from 0 up to the maximum of three things. So the maximum of the, let's say, of two vectors, or whatever values are found in two vectors, and those are the vector of radial stresses and the vector of circumferential stresses. So that would be find the maximum between, this is redundant, but the maximum of the circumferential stress valued float. Yes, this is correct. This is what I want. Yeah. So in this vector, we're going to find the maximum value. In this vector, we're going to find also the maximum value, and whatever maximum between both of them is going to be the maximum of my horizontal axis. That's basically what this is saying. And then I'm going to have figure show. So let's give it a go. Fingers crossed. Oh, forgot a comma. Where? Name was scatter. Let's see. Red in line. Of course, I forgot a comma. Again, a comma. Where? Radius. Where in line? 9. In here, another comma. Well, what else? Do I need another comma? Well, let me put just a comma here, just in case. Let me see. Oh, here it is. Nice. So we have in blue the circumferential stress. We have in red the radial stress. And look at the shape, like we said it was going to be in the lectures. And look at this. So it goes from, this is 0, close to 0. This is 0, 4, 0. So this is 30 as we calculated. And then this is 129 plus 0.367 as we said. So, but look at this. So this is awesome. So now we have coded basically the way, let's say, a rotating thin disk with, let's say, internal hole should, let's say, the stresses on that element should be represented or are going to appear in this case. So look at this. And this is the maximum should be at 0.18 something, which it is. Oh, this is amazing. Yes. So there we go. So we can embellish or put these some other points. For example, we could say now, so where is the maximum radial stress, where is the maximum, let's say, circumferential stress. But you're going to see here that this is the way they look. So here on the horizontal axis, we have the stresses in pascals. Here in the vertical axis, we have the radius in pascal. So can I, let's see, copy this? Let me download this so we can plot it into neoplot.png to plot it into the example. So I should have downloaded it from clicking on the buttons there. So there it is. This is a plot. So this is the code. So let me just bring it. New plot, this one here, and then let's go back to OneNote. And there it is, our results. Nicely represented. How those stresses vary along the radial direction. Wow. Well, and this answers the fourth question, the last one. So I hope that you stayed with me until the end. I know that this way of solving the exercises was a little bit different from what we have done before, because we used a little bit of help with the coding, but we use it because it was just substituting these values here. Practicalities like the derivation, we did it by hand, although we could have done it with any other software, but we did it by hand because it's possible to be done in this case. It's not that difficult. We found the value where the maximum radial stress is going to be located along the radius by forcing this relation here. And what else? So we found the maximum radial stress, and we found how graphically a representation of the circumferential and radial stresses there. Very interesting problem. So I hope that it helps. I hope that you had new tools that you could use, maybe the Python part for your own, to create your own library, to have it with you at hand, and then you could use it if you have a need to solve these type of problems in the future, because it helps. So I'm going to say goodbye now, and then we will come back with another exercise of this. Thank you.